It's time for the second talk this morning, and it gives me great pleasure to introduce Domenico Cantone, who will tell us about an overview of computable set theory, foundations and recent advances. Please.
Hi, good morning, everybody. First of all, I want to thank Alessandra Parmigiano for this great job, for inviting me here. It's workshop. We'll do a brief overview of the computable set theory, as the title says. First of all, let me remind which is the main problem in this area. We are interested in the decision problem for given collections of formulae of set theory, which we call fragments from now on. And this is the problem of establishing algorithmically for any formula phi in the fragment, whether or not phi is true in the von Neumann universe of sets under every set assignment. If it is true under some set assignment, it could be said to be satisfied. Briefly, the von Neumann universe, also known as von Neumann cumulative hierarchy, is the class V of all sets, which can be constructed in stages, starting from the empty stage V0, iterating the power set operation. We construct all the stages. There is a problem with the limit ordinals. At this stage, we just take the union of everything that has been constructed so far. Okay. The body of results in this field has been named computable set theory since the very beginning. And rather than the validity problem, the interest has been mainly focused on the equivalent satisfiability problem, namely the problem to establish whether any formula in a given fragment under study is satisfiable or not, namely if there exist variables, there exist sets which, when substituted to variables, make the formula true. Where all this started? Well, in the early 1970s, at New York University, Jack Schwartz and his group developed an experimental, very high-level programming language called CETL. Did anybody in this room heard about CETL? Okay. CETL uses set theory as a common language for algorithm specification and program verification. And what is incredible, it allows programmers to write code just as they think. Since CETL has sets and finite maps as primary data structures, and it has a construct of set comprehensions, which allows to construct a set through a declarative expression, closely mirroring standard mathematical notation. And it handles also quantifiers and both universal and existential quantifiers. It has a lot of other very interesting features. So often one can write single line code to express algorithms that otherwise would require several lines of codes in other programming languages. Unfortunately, Settle didn't have a good fortune and has not been maintained. But there are languages currently in use which can be seen as the descendant of Settle. The most one of the most used currently is Python, which somehow treats sets much as in Settle as Settle did. And so in the late 70s, again, Jack Schwartz and this group, which at that time was a group on computational logic, which at the time was formed by a few Italian people. One of them was my advisor for my undergraduate degree, and envisaged a semi-automated proof checker based on set theory, which would allow to help improving program correctness, mainly for programs written in Settle, as well as extensive formalization of classical mathematics. And the idea was that the inferential kernel of such proof verifier would embody decision procedures which were intended to capture what is regarded as obvious. Must say that the group of Italians at the time were from mathematics, had a mathematical background rather than a computer scientist one. So the interest soon shifted rather than on the implementing this proof verifier on trying to identify the boundary between the decidable and the undecidable. So it shifts to some foundational quest. So this research started in the late 70s, and the first fragment which was taken into consideration was called MLS, which is an acronym for multi-level syllogistics. It involved membership, so this is the reason why talk about multi-level. At the time, some fragments were already studied, but they had two types of variables, one for elements and one for sets. So those were really two-level, kind of two-level syllogistic. Formulae of MLS are propositional combinations of literals of, oops. Going well. I lost. Okay, yeah. Of these four literals of these four forms. We have binary union, set union, binary intersection, set difference, and membership, and also their negations and their combination using the propositional connectives. First extension of MLS involved also the study of the singleton operator. So in 1980, the first paper of a series that eventually would have arrived at comprised 17 papers came out. Some of the extension which subsequently were proved decidable involved enriched the MLS kernel with unary union, which is intended as the union of all the elements of the argument, unary intersection, the intersection of all the elements of the argument, some rank related constructs, the power set operator, the power set and the singleton operator. This was a very technical result, which, by the way, was the topic of my PhD at NYU, and more recently an extension with finiteness predicate. I also mentioned other extension of 2LS with map-related constructs, topological constructs, and graph-related constructs. This is also some current work. What I wanted to say here, I don't remember, so I'll say it later in case. The body of results have been collected in 4 monographs, and a 5th one it will come up in 1 year or 2. I was talking about the boundary of decidability and undecidability. If we add to MLS Cartesian square literals of this form, and also cardinality comparison literals of this form, the satisfiability problem of this extension becomes undecidable, because Hilbert's 10th problem can be reduced to it. I recall very briefly the Hilbert 10th problem. Given a multivariate polynomial with integer coefficients, it asks for an algorithm that decides whether the Diophantine equation p x1 xn equals 0 is an integer solution. Martin Davis was one of the professors at New York University at the time, was devoted several years on this problem. And together with Putnam and Robinson, they reduced the problem to the following conjecture. If the exponential function or equivalently any function which grows very fast could be represented by a Diophantine equation, then one could show that every recursively enumerable set is Diophantine. And from this, it would follow the Hilbert's problem is undecidable. So the only thing which was missing was that exponential function could be represented by Diophantine equations. And Martin Davis predicted that a young Russian mathematician would eventually show this last step, and so it happened. In 1907, at the age of 23, Yuri Matyasiewicz proved that every recursively enumerable set is Diophantine by showing that the Fibonacci sequence can be represented by suitable Diophantine equations. And Russian obviously give all the merits to Matyasiewicz, but it is fair to call this theorem as the Davis-Putnam-Robinson-Matyasiewicz theorem. By the way, Matyasiewicz also wrote a book on this on the subject in 1993, which was rewritten. It was very recently translated also in Greek. Go ahead. Okay, let's go back to multi-level syllogistic. And initially, there was we were not very much interested in complexity issues. So only in 1988, it was proved that the satisfiability problem for MLS and its extension MLSS is NP complete, even if one restricts to conjunctions. Obviously, in presence of connectives, one cannot hope to get a lower complexity. But even if restricted to conjunctions, the problem remain in NP, and it is NP hard. So all extension of MLS are NP hard by Netflix. In fact, it has been observed quite recently in a paper co-authored also by our Andrea De Domenico, which has been observed that even if we further restrict ourselves to conjunctions of literals of these two types alone, we hit NP completeness. Despite this complexity, the decision, the implementation of the decision algorithm for MLS, even for an extension, has been implemented in the form of semantic tableau, quite efficient one, and it was made available in the proof checker Etnanova. And also I know that in the step verifier at Stanford and in Lean, I think it was included. So as a settle, also Etna Nova remained at the level of a prototype. Here is a screenshot of a proof scenario of the Zermelo's principle that every partition has a choice set. So by analyzing various proof scenarios developing in Settle, some of which fully formalized, also starting from the barest just from the empty set, formalized the integral Cauchy integral theorem. It became apparent that several uses of the algorithm for MLS really concerned subformulae which might have been treated with more efficient procedures. And this is the reason why in recent years, rather than trying to extend MLS with more and more complex operators, we inverted the direction, our direction, trying to identify useful small fragments of set theory, so sub-fragment of MLS, most of which we found admit polynomial time decision procedures. So we distinguished between fragments involving the membership of relator and the fragments in which the membership of relator was dropped. This last fragment belonged to theory which we called Boolean set theory, and it involves here I keep go back. No. Here. Anyway, so it involves the usual Boolean operator, the Boolean relators of inclusion, set inclusion, and equality and their negations. Also, the predicates set is empty, or the binary predicate to given sets are disjoint in their negations. So if we call this, we denote this theory in this way by listing all the ingredients, we can, using much the same notation, we can consider sub-fragments where we list all the operators available and the predicates, or the operators and predicates available in the fragment, where the operators are drawn from the collection of the binary set operators and the predicate symbols of, from the collection of the predicates I showed earlier. Okay, so Okay. What we mean here by set assignment is any map which sends a collection of variables, the ones that occur in a given formula for which we are interested in its satisfiability into the von Neumann universe of well-founded sets. And this map is then extended by putting for terms S and T, M of S union T is equal to the union of MS and MT and MT, and so on. And then concerning the interpretation, M of S equal empty is true if M of S is empty. M of disjoint S and T is true if M of S and MT are disjoint, and similarly for the remaining operators and predicates. And given a conjunction and a set assignment M over its variables, M satisfies phi if M phi is true. A conjunction phi is satisfiable if it has some model in the sense I said. Otherwise, it is unsatisfiable. Despite these fragments are very simple, they can express conjunctions that are not obvious at first sight. For instance, the following three conjunctions are unsatisfiable, and this is not completely obvious. So it is useful to have a system to put them. So what we did is to study all the fragments of BST and to find out the one that are NP complete and the one that have a polynomial satisfiability problem. In the overall, since we have three operator and eight predicates, we have 2040 subfragments. Fortunately, it turned out that the majority are NP complete, but there are 762 which are polynomial. Fortunately, we didn't have to analyze each of these 2000 because it was sufficient to identify the minimal NP complete fragments, namely the NP complete fragments that do not strictly contain any other NP complete fragment, and the maximal polynomial fragments of BST. And since any other fragment is either contained in a maximal polynomial BST fragment or contains some minimal NP complete fragment. And it turns out that there are 18 minimal NP complete fragments and 5 maximal polynomial fragments. So this table shows the various fragments. So how can we make use of this portfolio of fragments. Assume, for instance, that we want to show that the power set of A union the power set of B is contained in the power set of A union B. Then in a interactive proof verification system, we can negate this formula and try to show that this negation is unsatisfiable. So the first, to show that the union of PA and PB is not contained in the P of A union B, it is sufficient to beat an element which belongs to the first set but not to the second, which is equivalent in this case to say that there exists a subset of A or a subset of B which is not a subset of A union B. This reduced to testing the unsatisfiability of these two conjunctions. Each of them belongs to this fragment, which is, as we show, as an n-cube decision procedure. So in time n-cube, we can verify that the unsatisfiability of both these two conjunctions, and then by using the step, which the human-aided steps that we did before, we can deduce that, in fact, this is true, and therefore it is a theorem. Here is another example about the distributivity of union over the intersection. Again, we try to negate. We negate this formula and try to check its unsatisfiability. In this case, we have the problem is more complex than the interaction is more complex than the one before, because so we again an equality is between sets is true if the two inclusions, these two inclusions are true, or taking the switching to unsatisfiability if and only if the negation of the disjunction of the negation of the both inclusions is unsatisfiable. So the problem reduces to showing that the following two formulae are unsatisfiable, these negative inclusions. The first one, both formulae belong to this fragment, which unfortunately is as an NP complete complexity. So how to reduce to polynomial complexity? We need to interact with the system by reducing this to a formula like that, where S plays the role of an element which belongs to the first set, but not to the second one. But in this fragment, we do not have a membership. So the role of this element is played by a small, say, a small set. We think of it as if it were a singleton set. Which and so we can say that S is not disjoint from this set, and if it is not disjoint, then it is, since it is small, it is wholly contained in it, but it is disjoint from both the first and the second conjunct. So we get a formula of this type, which you can analyze it and reduce the problem to formulate in the fragments in the fragment VST with intersections, disjoint and disjoint predicates, which has an n to the 4 time decision procedure, whereas the other formula A2 belongs to this fragment, which is n cube time decision procedure, and eventually in polynomial time we can prove that our formula is unsatisfiable. This was the first of the two goals. For the second goal, we can do much in a similar way and show that it can be shown to be unsatisfiable in the cubic time. One of the main tools in building the taxonomy we showed before is expressibility. A formula is said to be expressible in a fragment P if there exists a conjunction for which this holds true. But this technique, the expressibility notion was not enough. So we needed to introduce another, a more powerful, a more general notion of expressibility, which makes use also of complexity parameter. In this case, given a formula psi, which typically involves a construct that one wants to eliminate, this is said to be OF expressible in the theory T if there exists a mapping which, given a formula phi for which we want to test phi and psi, it produces another formula big psi such that produce this formula in time of f of phi, such that the first this conjunction is if it is satisfiable, so this other conjunction is satisfiable, and convert, and also every model of the first of this conjunction is a model of this one. This is condition C could be relaxed by saying that if this formula is satisfiable, then so is the other one. But we prefer to strengthen this request, because in this way we have a kind of constructive expressivity. This notion has further been generalized. And by the way, simple expressibility is reduces to O1 expressibility. This notion has been generalized further for collection of formulae, but we skip this. And these are some of the expressibility statements that one can do. In particular, X equal empty set is not expressible in this fragment, whereas it is ON expressible in a sub-fragment of that. So this shows that this notion is stronger. Here is an example of one of the reduction of resets for showing that the satisfiability problem for this fragment is incomplete, but we will skip on the details. Also, another family of formulae has been studied. Sorry, here I want to say that some other fragments which are not here it is. Some fragments which are not maximal polynomial have been studied, because for these subfragments one can find also more efficient decision procedure. This, for instance, is are subfragments of cubic or fragments which have a decision procedure of the fourth power of n, but for them we have a special decision procedure which are linear or quadratic. I skip on this. Okay, I wanted to conclude with some words on some current research. One of my obsessions since the early development has been the Cartesian product, namely to prove to solve or prove that this decision problem is unsolvable of m extended with the Cartesian product, the one which is quite close to undecidability. In fact, Martin Davis thought that this fragment as an undecidable decision problem. It can be seen as a sort of set theoretic companion of Hilbert's problem, where in place of numbers one has set, in place of sum one has union, in place of product one has Cartesian product. ordered pairs can be represented in several times, in several ways. So if we prove that an extension of MLS using one of the representation of ordered pairs is decidable, it wouldn't be granted for sure that with other representation the same would hold true. So a first step in this direction has been done very recently by proving that the extension of BST with the unordered Cartesian product. So the unordered Cartesian product of two sets is the sets of all the unordered pairs, where one of the elements taken from one set and the other element is taken from the other set. I denoted the unordered Cartesian product with product in a circle. This result is a big step towards the solution of the problem MLS with Cartesian product. Though is not definite yet. For the following reason, BST does not involve membership, and the Cartesian product here is unordered. But we can overcome the second problem because we found out that the decision procedure for this extension can be generalized to a class of operators which we call the factorizable operators. These are the definition so far is very involved, so I hope that to simplify it a little bit. But this class of operators include obviously the unordered Cartesian product upon which it is inspired, but all standard variants of the ordered Cartesian product, Kuratowski, Wiener, as well the power set and its indexed variant, which is defined in this way. P sub I of x is equal to the collection of a subset of x whose cardinality belongs to I, where I is any subset of n. Once we prove that we came up with a definite definition of factorizable operators, then using the notion of formative processes which has been developed when handling the decision procedure for MLS plus the power set and the singleton operator, it should be possible to to come up with a proof of the decidability of MLS with Cartesian product. At the point I can retire. Okay, I think that's it.
Have you tried proving the undecidability for with Cartesian product using trying to encode the theory of the word problem for semigroups, which is known to be undecidable?
So just the extension of MLS with Cartesian product.
Yeah, well, Cartesian, I would use the Cartesian product to encode semigroup operation, semigroup multiplication.
Well, I didn't try it because I strongly believe that it is decidable. So my heading towards the decidability proof.
Okay, well, commutative semigroups, which would correspond to your unordered product, would correspond to it is known to be decidable. So theory of commutative semigroups is exponential space complete, but theory of semigroups is undecidable.
Yes,
that's a difference between those two word problems is analogous to the difference between your ordered and unordered Cartesian product.
Yes, I think that I think that it will not possible to encode semigroups, much as you cannot encode the integers without having a cardinality comparison. So this is what I think, and so you agree with Martin Davis at this point?
I'm not going to conjecture anything.
Okay. No, we are very close to prove the decidability. In fact, it's just a matter of checking the technical details. So I didn't give any technicalities here because it's under development. So they are more, I assume, more cumbersome that it need to be. But I'm very confident that about the decidability of MLS with the Cartesian product. If I fail, I will.
Yeah,
I will use your suggestion. All right. Okay.
Yes.
Hi, thanks for a very nice talk. You mentioned some of the early NP hardness results by reduction to SAT. At some point, at least with some 3 SAT in some case. Would it be reasonable to think about reasoning on these things, or at least the validity problem, say, by thinking about, I'd say, proof theory on classical logic for some fragments, certain fragments of classical logic? Just by using the analogy, the reduction to SAT and then the core problem.
Yes, I think so. Though the barrier of NP completeness will not be broken, but one could use, for instance, heuristics developed in that field to prove in favorable cases what one has in mind.
Right. So I specifically meant using, say, proof theory for say classical logic, where you have some way of organizing your arguments to, for example, show it's in co-NP, for example. You see what I mean? Like you take the problem, if you can reduce it you can reduce it to a set problem, which means the complement reduces to a co-entry problem. And if you could study that as via the proof theory of classical.
Yes, I think so. Very good question.
Let's thank the speaker again. Another short break, 2 minutes. That's really good.